Hello everybody! Alrighty, in this video we are going to get into polar equations. So first I need to kind of remind you guys of some of the pre-cal concepts that you may or may not have gotten depending on what pre-cal you were in. But let's talk about what polars are. So just a reminder, rectangular coordinates are in the form xy, right? So we go an x distance and a y distance to get to whatever point we have. A polar coordinate is in the form radius theta. The theta is based on your unit circle angles, and the radius is the distance from the center. So if I really wanted to, this isn't something that we're going to do, but I'm just trying to help you guys make connections. If I have, what you see right here is a polar grid with all of the circles and everything like that. So here is a circle with a radius of 1, radius of 2, radius of 3, or depending on how you scale it, it could change. Right? Notice the angles that you see are related to your unit circle angles. That is in the position of pi over 6, pi over 3, pi over 2, 3 pi over 2. Negative angles still go backwards, so 11 pi over 6 could also be negative pi over 6. Right? These things go on forever in both directions. If you're looking for a pi over 4 is right in the center, such that it is right in between 0 and pi over 2. All right, but if I wanted to, right, so I could superimpose an x and a y axis on this, and say I want to talk about the point 1, 1. I think it will be right here. So this blue point, if I express it as rectangular coordinates, that is 1, 1, right? Over 1 unit and up 1 unit in the x and y direction. If I wanted to express this as polar coordinates, the radius I can get from Pythagorean theorem, since this is a triangle with a base of 1, height of 1, the radius here will be root 2, and it is acting at an angle of pi over 4, since it is a 1, 1, root 2 triangle. So this coordinate can be expressed in both rectangular and polar form. We're going to be mainly focusing on polar, going back and forth somewhat just to kind of help you guys understand everything, but I want to take a second and just graph these points where they are. So the first point, A, usually what I do, and these are kind of backwards to me, because usually the angle is going to be our independent variable. Usually. Not always, but usually. So if I put in 2 pi over 3 into a formula, usually that'll come out with a radius. You'll see these in just a minute too, though. But I go to 2 pi over 3. That is right here, right? So I'm thinking about on this line. And the circle with a radius of 4 will be 1, 2, 3, 4. So this is my point A right there. That's it. That's the point. All right. Moving on. Get rid of that stuff. Let's see, the point B is at the angle 7 pi over 6. So I'm thinking about this line right here. And a radius of 3. So I'm at 1, 2, 3. So I should have a point right here. That is my point B. Then the next one, I can find 5 pi over 4. 5 pi over 4 is right here. But the weird thing about this is the radius is negative. So this 5 pi over 4, the red line right here, is if I'm going out positive radii. If I have something negative, all that it will do is go the complete opposite direction. So instead of being on positive 5 pi over 4, it will go 180 degrees, or pi radians, the opposite direction, and it will have a radius of 1, 2, and it will be at this point right here. So again, still 5 pi over 4, but it goes the complete opposite direction, stays on a straight line there, at least as straight as I can draw it. All right, my last point here has negative pi over 6. So like I said in the kind of introduction of this stuff, this is the same position as 11 pi over 6. So negative pi over 6 goes the opposite direction, and a radius of 1, 2 will put me right here at point D. So there's lots of ways to express these things. There's actually at least 4 different ways, 4 unique ways I can express every point. But we'll get to that in a minute too. All right, so in pre-cal, for sure, 100%, we did talk about this stuff, where if I have a triangle right, with some angle based on the unit circle. It travels in an x and y position, and this is the radius. This relationship is kind of how we've determined the relationship between xy and r theta. So cosine is adjacent over hypotenuse, so x over r. So x will be r cosine of theta. Sine is y over r, so y is r sine theta. Tangent is y over x. X squared plus y squared is equal to r squared, so r equals the square root of x squared plus y squared. These first three relationships are the most important. This one is one that you need to know. You need to know this one, and you need to know this one. I haven't seen the tangent one come up quite as much, but I have seen it on free response in the past years. But for sure, these two right here will be used. You will see those on your AP test, at least how we use those in calculus. All right, but those relationships kind of help us move forward. So convert 2 and 5 pi over 6 to rectangular. So that means this is a radius and an angle. And just like we talked about, x is equal to r cosine. So all I need to do for my x is say, hey, this is 2 cosine 5 pi over 6. And y equals r sine, so 2 sine 5 pi over 6. If you did physics, you probably did r sine, r cosine in your projectile motion formulas, if you remember that. If you don't, it's no big deal. We're doing it now. All right, but we can evaluate these things. Cosine of 5 pi over 6 is negative root 3 over 2, so this will come out as negative root 3. Sine of 5 pi over 6 is 1/2, so this will come out as 1. Question sometimes comes up, do I need to simplify this? This isn't really a question that you'll be asked on the BC test. Knowing it will help you in graphing these things if you need to, or if you need to think about the graphs. But no, you could leave it technically as this in free response, but multiple choice, they will use the unit circle and they will write that out as negative root 3 comma 1. All right, convert negative 3 to polar coordinates. One thing that I will want to know is where it is. That was bad. So if I have a grid that I'm thinking about, negative 3 is down here. So I need to know a radius. Well, the radius is x squared plus y squared. Right, so r, 9 and 9 makes 18, so r is root 18. And I need to know an angle. Well, I can get the angle by doing tangent if you want to. Y over x, so negative 3 over 3. So this theta will come out as negative pi over 4. It could also come out as 3 pi over 4. And then there's other things all the way around. We could have 7 pi over 4. Right, so that's the same position as negative pi over 4. But I'm going to list this as either negative pi over 4, 7 pi over 4, and that 3 pi over 4, I can actually use that if I make my radius negative, just to get you guys thinking about this, which means I can also have negative root 18, negative 5 pi over 4. All right, all of those will be in the same position because the 3 pi over 4, the negative radius will flip it the other direction 180 degrees to that point right there. Okay, convert the following equations to polar form. So y equals 4. I know this line is a line something like this, right? And I know y is r sine of theta. So I have r sine theta equals 4. That is the same equation in polar form. Super ugly 4 though. And just to show you, in your calculator, because they're either going to give you a graph of these things when you have to do them, or they will give you a calculator to help you kind of figure them out. So if I go to my mode and I change this to polar mode, when I go to my y equals, if I'm trying to graph something, whoop, get out here. Notice that they are all r equals. So looking back at our problem, I probably will want to make this r equals 4 over sine theta, so that I can type 4 divided by sine theta. And if you hit your xt theta n button, which is right next to alpha, right? It's that one in red right here. If you hit that button, that will change based on what mode you are graphing it in. So if you're in function mode, it'll be an X. If you're in parametric, it'll be a T. Polar is going to be a theta, and sequential, which I've never used before, I'm interested in though, will be an N. But now if I look at my graph, it is a straight line at y equals 4, just like I thought it would be. All right, so this next one, x squared plus y squared equals 25. Well, x squared plus y squared is r squared, so r equals 5. And I know from geometry, and a little bit of pre-cal, we did a little bit, that x squared plus y squared equals 25 is a circle. That is not a circle. Come on. A circle. Centered at 0, 0 with a radius of 5, which is the same thing that this is telling us. It is a circle with a radius of 5. That is an equation I want you to be able to graph without having to put it in a calculator. That's not a circle. There's a circle. All right, so that's a circle with a radius of 5. All right. Now a little bit more annoying. R sine theta equals 3. Well, if I think about this, R sine is just y, so this is just y equals 3. So I have a line something like this. R equals 2 cosine. Pretty soon, I'm going to want you to be able to recognize that this is a circle centered at 1 on the positive x-axis. Cosine is related to x, sine is related to y. So let me show you a few examples here. So I'm going to make it big. I'm going to do 4 cosine of theta. This will be a circle with a diameter of 4 centered on the x-axis, right? If I make this a negative 4, all it does is reflect it over to the other side, because those radii would just become negative. If I make it 4 sine of theta, sine is related to the y, so it'll be a circle with a diameter of 4 on the y-axis. And if I make it negative, it'll be on the negative y-axis. Those 4 equations, really 2, because the negatives just reflect it, as well as r equals 5 or 10 or something like that, I want you to recognize as a circle with a radius of 10. Those 3 things you should be able to do without a calculator by the time you get through this stuff. All right. So converting this, I want to turn this into an x because it kind of looks like an x. So what I can do is I can multiply both sides by r. So r squared becomes 2r cosine theta. And r squared I know as x squared plus y squared. And r cosine is just x. And then if I do some algebra 2, algebra 1 skills, and I complete the square, subtract the 2x over, complete the square, this becomes x minus 1 squared plus y squared equals 1, which gets me to the formula that it is a center of 1, 0, and a circle with a radius of 1, which is exactly what I see. But it's represented much more simply in polar form. All right, theta equals 2 pi over 3. Well, 2 pi over 3 is right there. And this is only for positive radii. Like we were talking about, if it was a negative radius, it would just go the complete opposite direction. So I would have a line altogether, something like this. Now, how do I get to express that as a line? Well, if I take the tangent of both sides, tangent I know is y over x, and tangent of 2 pi over 3 is, let's see, opposite over adjacent, so negative root 3. Right, so then that means y equals negative root 3x. Right, and there would be the equation in rectangular form. Okay, so this is all good and all, but what are we going to be doing with calculus with this? Because we've just been doing a bunch of like converting things. I'm just trying to help you understand things. But what I want to do next is we're going to be like taking the derivatives of things. So if I wanted to do, well, let me do x. Say I wanted to take the derivative of x with respect to theta. What I would need to do is treat this like the product rule, since I have r times cosine of theta. So this would be dr d theta times cosine plus r times negative sine. And then if you really want, you would have a d theta, but that would divide to make 1, since I'm taking the derivative with respect to theta. Right, so this would mean my dx d theta would be r prime cosine minus r sine theta. If I wanted to do from y r sine theta, and say I want to find the change of y with respect to the angle, this would be r prime sine plus r cosine of theta. Now, what if I wanted to find the slope of the tangent line? This is going to be just like parametrics, where if I'm looking for dy dx, I can take dy d theta and divide it by dx d theta to get dy dx, right? So that's what I have written off to the side here. Dy d theta divided by dx d theta is equal to the slope of the tangent line at whatever angle you are using. So we can turn this into, some teachers make their students memorize this. I do not want you to memorize this, but I do want you to memorize that x equals r cosine, y equals r sine, and then you can come up with it. Over r prime cosine minus r sine. Right. Okay. So now, whoop, that didn't delete. Thought I cleared all of this. None of it deleted. It's terrible. All right, I'll delete here in a second. So we're getting to the end of day 1. It's been about 17 minutes, which is why this is the first day. So if I want to find dy dx and the slope of the graph at the given value of theta, so the given value of theta is pi. But first we will need to find dy dx. So what I like to do is I like to say, hey, y equals r sine theta. So that means since r is 3 plus 2 sine of theta, this becomes 3 plus 2 sine theta times sine theta. Because this is what r is, right? Yeah, that's just replacing that. Okay, same deal for x, but x is r cosine, so that becomes 3 plus 2 sine cosine theta. And now for dy dx, this is why I don't memorize that formula, because I know all I need to do is take the derivative of this and put it over the derivative of this. So 3 plus 2 sine theta, the derivative of that is just 2 cosine, and then times sine, plus 3 plus 2 sine times the derivative of sine, which is cosine theta. All of that over, right? With that, I was using the product rule, this times this. So the derivative of the first was here, times the second, which was there, and then the first times the derivative of the second, so the first times the derivative of the second. Same deal down below. 3 plus 2 sine theta, the derivative of that is still 2 cosine theta. Those do not divide out, do not try to divide those out. And then I'm going to put minus since I know the derivative of cosine is negative sine. So 3 plus 2 sine theta and sine theta. Now if I want to evaluate dy dx when theta equals pi, then I have 2 cosine of pi is negative 1, so this is negative 2. Sine of pi is 0, so times 0, plus, and then I have 3 plus 2 times 0, so just 3. Cosine of pi is still negative 1, over negative 2 times negative 1 minus 3 times 0. And that will simplify, since I can lose my negative 2 times 0 and 3 times 0, to be negative 3 over positive 2. And that would be the slope of my tangent line when theta equals pi. All right, I'm going to take a second and clear off all this stuff so it's not there and I can talk to you. 1 minute. All right, so the next thing that we're going to get into, now that we have talked about differentiation, the other idea in calculus is integration. So I need to find the area under the curve safe. Now, this is my pole. The pole is just 0, 0. That is what it is called. And I want to find the area of the shaded region here. So this region R. Now it's important to remember that my distances are measured out. The radii are measured out to the curve. And just like in the xy plane, in order to approximate this, right, if I wanted to approximate this in the xy plane, we did a rectangular approximation, right? We did Riemann sums. So say I wanted to do a midpoint, it would go something like this. Whoop. Right, and then I could add all of those areas together. And the smaller that I made those rectangles, the better my approximation became. So it's the same idea here, except I want to add little tiny sectors of a circle. So I need to be able to find, how do I find the area of this sector of a circle? It's just a part of a circle. So let's talk about that, because apparently you didn't learn this in pre-cal. I think you did. I'm pretty sure you did. But say I want to find the area of a part of a circle. Well, I know the area of a whole circle is pi r squared. Well, I want to do a part of a radian out of a full 2 pi radians. So the area, and it's called a sector, if I multiply up that pi r squared, right, the pi's will divide out, and I'm left with 1/2 theta r squared. So that is just one little tiny sliver. And I want that little sliver to become smaller and smaller and smaller and smaller, and add all of those up from my first angle to my last angle that I'm adding. That brings in the integral. The integral will take care of this change in the angle. The r squared will be ever changing, but that's going to go into our formula for our integration. So the area will be equal to, I'm going to factor out that 1/2 from theta 1 to theta 2 r squared d theta. 1/2 theta r squared represented as an integral. That is all that our area formula is going to be. So from the first angle to the second angle, the area between those two angles. Okay, all of this was kind of just coming up with that. You can read it if you want, but that's how we get to this formula. All right, so the next one here, again, you're going to be either given a graph or you will be given a calculator. So we're going to work with a calculator today because I want you guys to get used to the calculator. So again, we are going to be in polar, so check that you are in polar, check that you are in radians. So to graph this equation, I'm just going to type in 2 plus 2 sine of theta. Something that you can do to make your zoom a little bit prettier, because usually you'll pull it up and it'll look something like this, but that's not really what the picture looks like, because notice your Y ticks are very much closer than your X mark ticks. And if you hit zoom square, it will make both of them the same amount of distance. So you'll actually see this as what it will look like. If you want to zoom in a little bit, you can choose zoom in, and then you press enter where you want to zoom in. I'm going to zoom out again, zoom 5, zoom in. Let's see if I can't center this a little bit better. So notice I'm moving my cursor. I'm going to move it to the center of the shape. And if I press enter now, then it is a much prettier shape and it all fits in my window. So it looks like I have a y-intercept at 4. So I'm going to put my y-intercept at 4. And then I have 2 and 2. And then it goes to 0. And it's kind of like this weird Among Us, right? Manga S? I don't know. Monka S? I don't know. I don't know what you guys are talking about. Okay, but I'm looking for the area enclosed by this entire figure. So what I would like to know is what angle do I need to encompass? How many radii do I need to add together? What I like to do is I like to pick a point. I would like to choose 0 because 0 is usually easier to solve for. So if I do 0 equals 2 plus 2 sine of theta, and I solve for the places that the radius is equal to 0, I can have negative 2 equals 2 sine theta. Divide over that 2, so sine theta equals negative 1. And sine theta equals negative 1 when theta is like negative pi over 2 and 3 pi over 2. All right, and you can verify this in your graph. If you do calc and you do value, I'm going to type in negative pi over 2. Oh, apparently it doesn't like it. Oh, because it's not in my window. Right? Yeah. Okay. Well, let's calculate 3 pi over 2 because that's going to be in the same position. All right, and that shows me it's 0. The other thing you can do is you can check your theta max. If I only want it to graph from 0 to pi, it only does half the shape. It does the top half of the shape. Let me see if I can do this here. You can also try to follow it. I hope this isn't too fast. The calculators we have in class, the one on my computer is like super wicked fast, except it doesn't respond to keystrokes very well. So I'm going to make this theta step 0.01, and hopefully it will go slow enough for us. Yeah, that's almost too slow. Okay. But it'll start graphing every 0.09 radians. And you can follow that little cursor as it goes around and see all of the positions that it goes. You also notice from the window, I'm going from 0 to 2 pi. That is how long it took to complete that entire figure. So if you wanted to, especially if you have your calculator, my area can be represented as 1/2 0 2 pi for this figure, r squared, 2 plus 2 sine theta, squared d theta. If you don't have a calculator, they will probably give you the bounds of the figure. If they don't, then this is the strategy that you need to go to find it. Because the area also can be represented as the integral from negative pi over 2 to 3 pi over 2, 2 plus 2 sine theta squared d theta. Okay, the other thing that we can do is if I went from, because notice on our graph, let me try to make it do it again. Right, so notice it's starting at 2, and then it's going to go around. If you press enter, you can actually pause it from graphing. But that is at 0 degrees at starting, and then it goes up to pi over 2 is right there, and then it hits pi, and then it hits 3 pi over 2, and then it comes back around and hits 2 pi. So notice the right-hand side is equal to the left-hand side, as in there is symmetry there about the y-axis. So if there is symmetry there, then I can do just half of the figure. So I could also represent this area as doubling the area from negative pi over 2 to pi over 2, 2 plus 2 sine theta squared d theta. So if you don't see like a 1/2 or something like that out front, you're like, hey, there has to be a 1/2. Check out your bounds, especially on multiple choice. They will do this probably at least once. Because this will give me the right-hand side of the figure, and then through symmetry, by doubling this area, I can get the area of the whole figure. Okay, let's move on. If my iPad will let me, you can do it, Mr. iPad. Okay, 2 sine 3 theta. I'm going to go ahead and graph that. 2 sine 3 theta. I'm going to pay attention to where it starts. Starts at 0, goes down, goes through, and I did 0 to 2 pi. And if you saw that, zoom 5, zoom in. Oh, I need to wait for it to be done. Notice it went around the figure twice, that little cursor. Once, and it goes around twice, and it completes the graph. So all that means for me, what I can probably do is do it from 0 to pi, and it will complete the entire figure. But, I mean, that's useful. Notice the radius is 2 there, so I'm going to graph it down to 2. And it did something like this, and this, and this. That's super ugly, but that's what it is. And I'm going to find when the radius is 0 again. So sine of 3 theta. So the angle inside for sine to be 0, there's a 2 there. For sine to be 0, though, then 3 theta must have been like 0 or pi or 2 pi or 3 pi, right, so on and so forth. And if I divide all of those by 3, then I get 0, I get pi over 3, I get 2 pi over 3, so from 0, let's check our graph again. Notice it starts at 0 and then it goes round. It hit pi over 3 right at 0. So if I am just looking for the area of one petal here, I could go from 0 to pi over 3. I could also go from pi over 3 to 2 pi over 3, or I could go from 2 pi over 3 to pi. I could also go from 0 to pi and divide the area by 3 if I know that 0 to pi is my entire figure. There's lots of ways of representing these things. So it's just whatever works for you in your mind. But the area here, I'm going to represent it, since it is of one petal, it is just talking about the area of one of these petals, as 1/2 0 to pi over 3 r squared, so 2 sine of 3 theta squared d theta. You could also double this area. If you did, the petals are symmetric about their central line. And that central line for this one will be pi over 6. So if I went from 0 to pi over 6, 2 sine 3 theta squared, d theta will give me the same area. So again, if you don't see that 1/2, just check your balance. All right, take a second, try this one. I'm going to go ahead and put everything up here, and then I will talk about, well, I'll just work it out. But try it. Pause the video, try it, see what you guys come up with. I'm going to go ahead and graph it. Oh, paused it. Y equals 4 cosine 2 theta. Cosine 2 theta. And graph. Oh, that doesn't look like everything. I'm going to zoom out just a little bit. Yeah, and if I change my window from 0 to 2 pi, that looks much better. If you're not sure what it looks like, you could make the window like 0 to 6 pi or something like that. But I know this is the complete figure here. Oh, yep, not pretty. You don't have to actually graph these things by hand. Again, they'll either give you a graph or they will give you a calculator. Okay, so if I'm looking for one petal here, I'm going to solve for when the r equals 0. So that will be when 2 theta is like pi over 2, 3 pi over 2, so on and so forth. But that's really all that I needed. And notice it started at pi over 2. And if you watch your graph, I wish I could zoom in just a little bit. I don't know how to do it fast. Okay, but if you watch your graph, notice it started at 4. That is because if I put in cosine of 0, cosine of 0 is 1, so this starts at a radius of 4. So I'm starting out there and I'm working back in. So this petal that's going from, when I solve this, pi over 4 to 3 pi over 4 is actually the petal below the y-axis right here. Starts out here and goes down here, and then it comes back around. I think it went up there, and then it does the top loop, and then the very last thing it does is complete that first loop that we saw, that first petal. So my area of one petal is 1/2 integral from pi over 4 to 3 pi over 4 r squared d theta. All right, and again, there's lots of different ways you can write that. Okay, so next, we are going to talk about the area between two polar curves. So for the area between two polar curves, first let's think about graphing them. So again, one of ours is 3 sine theta. I want you to be able to recognize that that is a circle on the y-axis with a radius of 3. All right, so there's my circle, r equals 3 sine theta. And then 2 minus sine theta, I don't expect you to know that, but we can graph 2 minus sine theta, 2 minus sine theta. I'm going to zoom in. It's kind of an elongated, like weird looking circle type thing. And if I look at my window, it's going from 0 to 2 pi. I didn't trace it any more than once, so I know my interval is 0 to 2 pi. But these circles, the 3 sine theta, that will actually complete in 1 pi. All right, let's see. I had 1, 2, 2, 3, weird elongated circle thing. Again, the graphs do not have to be very pretty. Mine is super ugly. But let's use this because we need to be inside 3 sine theta. So that is the region inside of my circle. So somewhere in there. But I need to be outside of 2 minus sine theta. So the part that is happening is this portion right here. And since my radial lines, in order to get my radius, it goes from the center outwards. So what I need to do is I can find the area of the entire circle, right, from this line to this line, that angle to that angle, and then I can take out the area of the inside, this 1 minus, this 2 minus sine theta, because that will go from there to there. I need to take out those areas. So my first battle is going to be figuring out where they meet each other. And what I would prefer to do is just take half of this figure, right, and use symmetry because the circle will complete in 1 rotation. The other graph, this 2 minus sine theta, took an entire 2 pi in order to be able to work back around to it. So it's going to be kind of weird if I go just from this line to this line because the circle will have gone more than that. It just gets weird. So I use symmetry to kind of help me figure out the area of these things. So it's going to be from whatever this is to pi over 2, right? Because that is when my figure will be straight up. So I need to figure out what that intersection is. And to find that intersection, I can figure out when the radii are equal to each other. So I have 2 minus sine theta equals 3 sine theta. That will become 2 equals 4 sine theta. So sine theta equals 1 over 2. So theta is pi over 6 and 5 pi over 6. Okay, so I think that would actually work out okay because 5 pi over 6, the circle hasn't completed 1 full rotation yet. And really, when the circle is on its second rotation around, the second time around, this graph is all the way over here. So I could go from pi over 6 to 5 pi over 6, and that would be fine on this one. But I'm still going to do it by symmetry. So my area, I'm going to double the 1/2 of the integral from pi over 6 to pi over 2 of the big radius, which would be the 3 sine theta squared minus the little radius, 2 minus sine theta squared d theta. Right? So this is still top minus bottom, right? Outer function minus the inner function will give me the area between the two. Okay, man, this is a lot longer than I was expecting it to be. So we got a couple more. This next one is kind of tricky, but with symmetry, it makes it a lot easier. So let's see, 3 cosine of theta is a circle on the x-axis with a radius of 3. All right, and then the other one was 1 plus cosine of theta. So I'm going to use my calculator for that one. Oops. And again, my window was 0 to 2 pi. So that completes a full rotation in that amount. And notice it started, my graph started way out here at 2, and then it went up to 1, came back around to 0, hit -1, and went back through the object again. So I have a sideways Monka S, or whatever. And I'm trying to find, in this case, the area of the common interior. So the area that they both share together. So I'm trying to find essentially this area and double it, because that is equal to the other common interior, which is right down here. The red and the green is what I need to find together. But I'm just going to find the red, because I know that starts from 0 pi for that one, and it is that equation. It's that 1 minus or 1 plus cosine theta all the way until the intersection. And then the circle takes over for just a wee bit for this interior area. It splits right at that angle right there. So all of these radians are the 1 plus cosine, and then these little parts right there are just the circle. So I need to figure out when it splits. Where is that happening? Well, again, that's when the radii are going to be equal to each other. So I'm going to take those two and set them equal to. So 3 cosine equals 1 plus cosine, which will give me 2 cosine equals 1, and cosine equals 1/2, when theta equals pi over 3 and 5 pi over 3. So this is an instance where if I use that 5 pi over 3, I'm including more than one go of that circle. This circle will complete itself after 1 pi. So if I go to 5 pi over 3, the circle will have gone around again and hit this at 5 pi over 3. Because this graph will still be over here. It doesn't hit over here until 5 pi over 3, so the circle's still like going around. These things are kind of weird, but you just have to think about how long it takes them to complete full rotations. Okay, so what I'm going to do then is from 0 to pi over 3, I have the first graph, which is 1 plus cosine of theta squared d theta. And I'm going to add that to pi over 3 to pi over 2. What's that, 3 cosine squared d theta. And notice I don't have the 1/2s, because again, I'm doubling that area. I'm doubling the area right here so that I can get the entire area of the full figure of the common interior. And that would be it. That's how I would leave this one. Okay, last but not least, this is something that will not be on your BC test, but it is something that I will put on a quiz, possibly the test, probably not. But you could very well see it on the quiz, hint, hint, wink, wink. You'll see it on the quiz. Okay, but the polar arc length, this is something that you could see in Cal 3, so I just want you to be prepared. Same reason we did the trig substitution stuff earlier in the year. But polar arc length, let me take you back to parametric arc length. Polar is very similar to parametric in the sense that it was dx dt squared plus dy dt squared dt, right? That was my parametric arc length. And parametrics are based on a parameter. Well, that parameter could have been theta, because I can treat polars as parametrics to an extent. So x equals r cosine, y equals r sine, and that will allow me to find dx d theta and dy d theta, and then substitute those in. So let's take a look at how that looks. Dx d theta is r prime cosine plus minus r sine, and dy d theta is r prime sine plus r cosine. So now if I want to put them in here, I want to square those things. So if I square both of these, right? And I distribute. This first one will become r prime squared cosine squared plus r squared sine squared. And then I'll have a middle term, where I have minus 2r prime cosine sine. Right. Same idea down here. So r prime squared. You don't have to know how to do this. I'm just trying to show you how that formula comes about. R squared cosine squared plus 2r prime cosine theta sine theta. Okay, so the nice thing here is since I'm going to be adding these two things together, I'm going to think about adding those two inside of my square root. The 2r prime cosine sine, 2r prime cosine sine will subtract out. If I think about my r prime squared, if I factor out an r prime squared, that would become cosine squared plus sine squared, which I know is 1. So that would just become r prime squared plus, same deal with the r squared. If I factor out a sine squared, or sorry, factor out the r squared, that becomes sine squared plus cosine squared. So this can become r squared. So that dx d theta squared plus dy d theta squared can be simplified to dr d theta squared plus the radius squared, which is how we come about this formula right here to measure the polar arc length for distance travel. So from A to B, the square root of r squared plus r prime squared d theta. So find the length from 0 to 2 pi. They give us the bounds of the cardioid 2 minus 2 cosine of theta. So it's really just as simple as long as you know the formula, plugging it in, 0 to 2 pi, square root of 2 minus 2 cosine theta squared plus r prime, which would be 2 sine theta squared d theta. And then I'm just going to type that in my calculator. So I'm going to use my integral shortcut, so 0 to 2 pi. And what I'm going to do actually is I'm going to type this in my r, 2 minus 2 cosine theta, and I'm going to make my r2 the derivative of r1 with respect to theta. So that'll do it for all of it, right? So that'll actually graph my derivative if I wanted my derivative. So there's my first, and then there's my derivative. My derivative is just a circle, which I could have known is just 2 sine theta, right? We had that written out. So cool that we were correct. Nice. And I want the square root of r1 squared. Didn't get the square root of r1 squared plus r2 squared d theta. So 15.99999, which means my answer would be 16 units. I should probably put the 0, 0, 0, 0, because I'm approximating and it is a distance, so units. Alrighty. And if you're wondering how to get to those shortcuts, it is if you press alpha and then F4, so alpha and then trace, that will get you your R shortcuts. You also have matrix shortcuts, which you won't really use in here. There's function shortcuts, which are useful for derivatives, integrals, absolute values, summations, log base, nth roots, and then these bottom ones you won't use much except for maybe your factorial. Then you have fractions if you want to express something as fraction, or if you want to turn a number into a fraction. It's not going to do it here. Let's say I have like 31 over 12. There it is as a fraction. If I want to express it as a mixed number, it first needs to do as a fraction, and then you will be able to do it as a mixed number. Useful sometimes, not always. I don't know. All right, this video is long enough. Hopefully it has been helpful. Talk to you all soon. Bye!